Right, so I'll make that 3 o'clock. So we'll start off and then hopefully gives a chance a few more people to join just whilst I'm doing introductions. My name's Katie Bridge. I'm from Scientific Laboratory Supplies. We're joined by Waters today, which is one of our new suppliers for this webinar on their DCR, their Discovery Core Rheometer. We've got Peter Hodder here, who's been with Waters for an incredible 30 years, joined in 1995. He's currently the application team leader. So hopefully he's full expert and there's nothing that he doesn't know on rheometers. And before his time at Waters, Peter graduated from the University of Birmingham and completed 8 years in industry. Just a couple of housekeeping bits before we start from me. We're anticipating the webinar to last for about 45 minutes today, which means we should have about 15 minutes for questions at the end. Because we've got dedicated time for Q&A, if you've got any questions, please save them to the end or put them in the meeting chat and we'll answer those. This webinar is being recorded, which has already started. What that means is that the session will be available to you after we finish today. You will get an email of the whole session, and the slides shared as well. What I'll do is I'll keep everybody on mute in the group, but as I said, if you've got any questions, please bob them in the chat or save them to the end. But I'll pass over to you, Peter, and we can kick on.
Okay, thanks, Katie. Hello to everybody who's joining us and those who hopefully join us in the very near future. As you've been understood, this is an SLS webinar series that presented by TA Instruments, part of the Waters Corporation. My name is Peter Hodder, as I've just been introduced, and I'm a Principal Support Specialist. And I'm going to take you on the next logical steps on the road to rheology. Now, I know that word rheology scares people, so I'm hoping that this presentation takes some of the mystique out of it. It's not going to get complicated. So let's then press on. So what I want to do in today's webinar, realistically, is remind you what you're probably already measuring, what viscosity actually is and the factors that affect it. I want to provide you with an overview of the concept of using the simple viscometers, remind you how they work, we'll consider the practical considerations and potential issues you might face or forgotten about. I'd also like to provide you with some simple introduction to other aspects of that word rheology that provides a more informed understanding of your products, whether that's how to simulate various applications, whether it's storage or high shear applications, and what happens afterwards, during a printing process, for example, or anything else like that. Or how can you explain the structural properties of samples like mayonnaise, ketchup, set yogurts, and so on. And obviously, at the very end, I'd like to introduce our Discovery Core Rheometer, the reason for this video, to show you some video demonstrations, performing routine tests, so you get a flavour of what it's like to work with the system. And then I'm also going to include a short video that shows the sample structure testing, so you can see that it's more than just a viscometer. So if you ask ChatGPT what viscosity really means, if you can see that on the screen, it basically says viscosity is a measure of the fluid's resistance to flow and deformation. In simple terms, how thick or sticky a fluid is. I prefer to say thick or thin. It also claims that there are types of viscosities. Dynamic, I'm going to refer to it more like absolute viscosity. This describes the internal resistance to flow. Usually it's in Pascal seconds, but for the sake of today, because most viscometers tend to like to prevent data in poise or centipoise, the old CGS units, you will see that I will say centipoise or poise. Obviously, there are examples that you might be very familiar with. Honey has a high absolute viscosity, water has a very low one. There is another viscosity some people mention, that's kinematic viscosity, and that links the absolute viscosity with the fluid's density. So basically, we talk about things called centistokes. Now, these tend to be more useful for people dealing with fluid flow mechanics calculations. Just some examples, just to give you a flavour, but water usually has 1 centipoise or 1 millipascal second at 20 degrees. Motor oils tend to range between 100 to 1,000 centipoise, and honey has a much higher viscosity, anywhere between 2,000 and 10,000 centipoise. Now, if you really want to know a little bit more about viscosity, then I'm going to suggest this little YouTube video that I've found from Ben Hansen, an associate professor at UCL. The link's there if you need it, but it just literally gives you an idea of why you would be interested in viscosity. So, remind ourselves what viscosity is. Well, Newton was the first person to really define the laws of viscosity back in the 1600s. He came up with the idea of taking 3 cylinders filled with the same liquid, had 3 little wooden boats, and what he did was he put 3 different weights on top of them. What he noticed was the heaviest weight sunk fastest, then the rate changed depending on the weight. And he came up with the equation that basically said the stress, which is to do with the weight, and the rate at which the boat sank seemed to have a linear relationship. And he defined the slope of that curve as the viscosity. So he came up with Newton's law of viscosity. Stress equals viscosity times shear rates. Most of us prefer to see it as viscosity equals shear stress over shear rate. Now, don't worry about that. It's just a ratio, etc. And we come back to more details of that maybe a little bit later. Anyway, let's keep it simple. Let's think about it. You're all familiar with liquids, materials that you can easily pour, decant, whether it's a pharmaceutical solution, water, or maybe an inkjet ink or something like that. At the other extreme, you've got solids, things like rubber tires and Lego bricks, things that basically stay in the shape and don't tend to move anywhere. And things that are in between tend to be called soft solids. Those are materials like glues, adhesives, creams and lotions, ketchup, and even to the extreme of things like set jellies and stuff like that. So what we've got is a material that can actually be very mobile and very low viscosity. We've got samples that are very high viscosity and don't tend to move, and something that's got a blend between the two. We can actually control the viscosity of the material for various applications. We should really consider what affects the viscosity. Now, if we think about actually how hard we shear it, stir it, or try to deform it, well, if we take honey, honey is actually a Newtonian fluid. It follows Newton's rule. Basically, it doesn't matter how hard you stir it or how gently you stir it. It's got the same resistance. It's got a constant viscosity. However, we take a sample like mayonnaise and put it in a bowl. We find the only way to get the mayonnaise out of the bowl is to squeeze it. We physically have to push it and apply a certain force to get it to become more mobile. This means the sample is actually a non-Newtonian. It's a shear thinning material. And this is where we start to see the reasons for moving from viscometers to rheometers. Other things we have to factor in is maybe how long we stir something. There is a thing called time dependency or thixotropy. And it's seen when the sample's resistance, its viscosity changes when you apply a constant shear. It will suddenly plateau off at a certain value, and then that's got rid of the even consistency through the material. The other thing that affects viscosity is temperature, of course. It is a source of energy, and so unless there's a reaction that's going to be initiated, most materials become softer, more mobile, and lower in viscosity as you increase temperature. We drain engine oils out of a car by warming the car up for a while, and then it's easier to drain out the oil. So, now you've got a reminder of what viscosity is all about and the things that affect it. Now we perhaps consider where you might be interested in looking at the viscosity, types of flow. Now, a flow might be simply through a pipe, down a tube, through production or anything else like that. It might be in your processing plant. It might be an application. It might be brake fluid to your brakes. It could be that it's going through a syringe or a needle, or even through a straw if you're drinking a milkshake. It could be that it's coming out of a tube or a dispenser, dispensing things out of like shampoos or pharmaceutical gels, topical gels, etc. And there's many, many more applications where it's going through some form of tube or nozzle. It could be that shear between two surfaces, a bit like the material we're seeing here, where there's a sort of like rubbing your hands together. That, of course, in real life is probably where you're going to see a nice spread in butter or Nutella on your toast. Or it could be a doctor blade and a substrate, or between rollers or the roller and a conveyor belt, just like this example of a gravure painting ink process. The ink is transferred onto the cylinder, but the excess is wiped off with a doctor blade. It's transferred to the paperboard that's going through, pressurized, and the conveyor printed issue paper goes off to be stoved and finally used in whatever form it needs to be used in. And of course, the final applications that most of us are familiar with is perhaps applying a cream, a lotion, or whatever, suntan lotion as the weather gets better this time of year. We see there's the cream between our fingers and the skin. And again, of course, there's many more examples. And finally, we shouldn't forget that there's actually flow under gravity. Gravity is a force and it makes things move. So you could end up with something just literally spreading out due to its own weight. That means that you can actually have self-leveling compounds and building materials. You could be looking at coatings like paints that you paint on the wall or on a piece of wood or anything else like that. Or you could be looking at adhesives or topical creams. You could be considering storage conditions like shelf life sedimentation, where you want to keep things evenly distributed throughout the body rather than settling like the Italian dressings in the middle or the clam chowder on the far right. And finally, you have to consider that there might be applications where you put something in a vertical plane and we see sagging, where things run down the wall. And we've all done DIY painting where we're trying to catch that run of paint before it hits the carpet or the skirting board. And again, there's many, many other examples I'm sure you can think of, dip coating, and various other things like that. So let's go back to thinking about our liquids, our soft solids and our solids, and think about actually applications that your sample might be going through. What you want to do is when you're applying it, you want the sample to act like a liquid because it's easy to move around. It's very mobile, low resistance. It's got a low viscosity, so it's acting like a liquid, easy to apply. You want it to act more like a soft solid, have something about it to offer some resistance to help with mixing processing or to give it controlled dispensing. Otherwise, materials come out the nozzle too fast, too quick, too furious. But obviously, it doesn't need to have too high viscosity because otherwise we're not going to get it out of the tube. And finally, we should think about it acting like a solid on storage because we don't want it to change. We just want it to stay exactly the same way when it went into the container so that when 6 months later we open the container, it looks exactly the same. No need for stirring, redistribution of the components, etc. So we have to have a sample that usually works like a solid and a liquid and something in between. And that's where the complication of rheology comes, because we have to have a sample having different properties for different occasions. Now, if you consider typical applications your sample might see, and I'm using the word shear rates here because those are references I would use in my training, but at very low shear conditions, we've got processes that are gravity-driven, like sedimentation and leveling. In the middle region, the green yellow represent things that happen under draining or pumping, so things that are encouraged to move. And then finally, at the highest end, we've got the mixing, the extruding and the brushing, the rubbing and lubricating, which are high shear conditions. Now, as I've mentioned, Newtonian fluid wouldn't change in any possibility. Its viscosity would be constant throughout this. But for a non-Newtonian fluid, we tend to get an idealized flow curve like this. At low enough shear, when we see sedimentation and leveling, we have a typical viscosity that's a low shear plateau. It's constant value until you exceed certain forces. Then you start to break down and go into what's called the shear thinning region. Now, the shear thinning region is where you're going to be looking at draining and pumping. So how easy is it to start to make the thing become lower in resistance so it's easier to pump, to dispense, etc. And finally, applications tend to be at much higher shear conditions and overlaps with the shear thinning region, where you're literally doing, as I said, the mixing or the extruding or the rubbing or anything else like that. Now, the interesting thing to factor into this is if I had a sample that I wanted to be very stable, I'd like it to have a high viscosity at low shear. But if I had a Newtonian system to work that way, the problem is that when it comes to being used as an application conditions to the high shear plateau, the viscosity would remain high and it would be very difficult to apply. Instead of using your fingers, you might have to use a trowel or something. And if we went for the other extreme and focused on the application end, we could have a Newtonian material that has the right viscosity for application, but also has the same low viscosity for storage, which means it's not going to be very stable and have problems with sedimentation, phase separation, blooming, or anything else like that. So now you can understand why it's important to have materials that have different properties at different occasions. And now we're going to see whether they can actually measure those with your viscometers, or you need something more. So I'd like to think about these steps on the road to rheology. Now I'm going to reference the Brookfield systems here because Brookfield are probably the best known brand of viscometers. You may have a different brand, an Ica or something like that. There's no disrespect to all, but it's just a case of using Brookfield because they use some nice video aids that help me demonstrate some things. So they talk about in their booklet more solutions for sticky problems, and basically a guide to getting the most out of your Brookfield viscometer and their own rheometers. They talk about these three schools: the pragmatic, the theoretical, and the academic. I'm going to walk you through each of these and then maybe make some other suggestions. So the first is the pragmatic approach, the first step on this road to rheology. Using a rotational viscometer, whether it's a Brookfield, ICA, or many of the other brands available, it's a motor-driven device that can use at one speed and measures the viscous drag resistance using a calibrated torque spring to give you a value. Now, there's usually multiple models available that have varying torque ranges. The springs differ between them, so there's low to high and something in between. And normally it involves using a lot of ranges of interchangeable spindles or rotors to really try and fine-tune the system to work to give you a measurement for the material you're trying to measure. You do also have the option for some of them to change different speeds as well, and I'll come on to that in a bit. As a result, looking at the portfolio for the Brookfields, you're at the low end in the price, but you're also on the low end for performance, from a dial viscometer up to something very simple. Now, the key point is I've just tried to outlay something here, but I think it's probably better if you actually hear from Brookfield themselves. So as I turn to the next slide, you're actually going to see an introduction to a video from the Brookfield Academy. There's a number of these YouTube videos freely available, understanding viscometers and how they work. This is part 1 out of 7. And later I'll share those links again to remind you that you can access these on your own to go through it. So I'm going to shut up and let this gentleman give you a presentation.
First, you need to understand the types of samples you're working with. It is important to characterize fluid sample flow conditions to identify the right instrument and test methods for successful viscosity measurements. You can determine the type of sample with this simple technique. Just check how it flows. Is the sample free-flowing, slow-flowing, or very slow to non-flowing? Let's assume the sample is free-flowing with low viscosity. In that case, I recommend using a viscometer with a low spring torque, big spindle, and higher spindle speed. The opposite applies to a highly viscous liquid sample. For these, a stiffer HA or HB spring, smaller spindle, and lower spindle rotation speed are recommended. The image on the screen shows the dial face of the Brookfield analog viscometer. I want to use this example to illustrate that all viscometers have the same principle of working from 0 to 100% torque. Torque is the twisting movement of a calibrated beryllium spring in the viscometer. If you look carefully, the dial face has 0 to 100 markings. 0% is when the viscometer is at rest. 100% is when the viscometer is measuring at its maximum. Anything beyond 100% is an overrange. So when you see a viscometer with EEEE, it means that it went over the range or beyond 100%. EEEE indicates that the sample is too viscous to measure with the selected spindle, speed, and spring range combination.
So what we're highlighting there is that you have to choose the right base model to start off with, then play with the spindles to try and get a resistance that was in the torque range and try to avoid going over torque. And what wasn't mentioned in that video is, though you have a full 100% torque deflection, they don't recommend you work within the bottom 10% either. So they talk about force torque ranges from 10% up to 100%. So that's a range of 90% to work with. Now, just to remind ourselves, what we're going to show you now is how you do a viscometer measurement.
Viscometer measure viscosity? Viscosity measurements are done by attaching a spindle connected to the viscometer motor through a calibrated spring and rotating the spindle while immersed in the test sample. The viscous drag of the fluid against the spindle causes the calibrated spring to deflect. The deflection is known as percent torque. It is measured with a transducer where it gets converted electronically. The test result is then displayed on the viscometer's LCD screen. The following factors determine the viscometer's measurement range: the test temperature, the spindle's geometry, the rotational speed used, the test sample container's dimensions and shape, and the viscometer spring torque.
Now, what I want to highlight there is there's quite a few variables that you have to consider and control. So just please remember that, because that's something very important. Now, remember that this was to be the first step, the pragmatic approach. And what you're looking at is viscous drag. And maybe you didn't understand what that meant. So I've just done a small video.
So in this example, what I'm going to try and use is a spindle number 5 from a Brookfield RV or LV. Difficult to tell because they all look the same, to be honest. I'm going to use some fabric conditioner and food dye just to try and highlight these sort of shear patterns that you can expect to get inside a beaker with the spindle, where we've got a massive gap between the wall of the cup and the edge of the spindle. So what I'm going to do is, normally you would fill up to the marker line on the system there, and you would submerge the spindle in at an angle so you wouldn't trap air bubbles, but I want to actually just fill it so that the spindle is just at the surface. Not an unusual way of being used, but a way to demonstrate, because as you can see, the Lenore fabric conditioner is coloured and opaque, so we can't see the spindle. It's submerged. I'm just going to pour enough in there just so that the spindle is at the actual surface. Now what I hope to do is drop some food dye on the top of the spindle and let it actually move to the edge and see where it spreads to. So you're going to have to bear with me while I start the motor and get this thing spinning. There is a black line on the shaft which hopefully you can just see periodically to show you it is rotating. And then I'm going to introduce by pipette some food dye onto the spindle, and let's see what happens. Right, I'll put it central, and off we go. So we're putting it around the edge of the spindle. So that's now been stirring for quite some time. As you can see, the red food dye has spread on its own accord using the Marangoni effect. But what I'm really focused is where the spindle is, and what you can see is as it's rotating there is a white band directly in contact with the spindle itself. Then there's a slight bigger red-pink ring around it, and if you look close enough in the white band and at the edge of the pink, you'll notice some droplets of food dye rotating. That's really indicating what I wanted to see, which is that there's a very localized shear around the spindle, and hence why using a spindle on Brookfield in a infinite C beaker like this really just shows that there's a localized shear, but you don't really know how much material you're shearing. If I decided to try and change the speed, so we're going to turn the speed up. It's clearly going faster now. Then again, you can see that the field will perhaps change slightly. That white band will expand ever so slightly. But again, we're not really certain how much of the sample we're stirring. And we're certainly not stirring the whole of the beaker.
So what I want to point out there is, for the first step on the road, the pragmatic approach, according to the booklet and everything else in Brookfield, what you're looking realistically is you've got a comparative method at best. You have to choose the right base model to start off with to ensure your sample actually remains and can be measured with the torque range available. You might can fine tune it with choosing the spindles and the speed selected, but basically you're going to be, for low viscosity, using the LV, for regular viscosities, the RV, and the stiffer materials that have to be HA or HB. Now there are other things we're going to talk about later, but very simply, most of these materials are still pourable and they're poured into a beaker of some form. What's very important is you must really specify in any measurement the viscometer model you used, the spindle number, the speed, and hopefully the temperature as well, to really be able to give comparative results across the company, across sites, across the world when you're comparing data. Now, I won't pretend that trying to understand how Brookfield's work was a little bit more. It's meant to be a simple device, but there's so many options. And one of the options I found very confusing is all the rotors, etc., and the speed settings and the torque settings and how they influence the data. So here's an LVT system. We're using RV spindles 1 to 7. if you remember, 1 is quite large and 7 is quite small. And what happens is that you design to use one of these, and what I've highlighted in red based on the speed limits of the system is the minimum speed you can expect, minimum viscosity, sorry, you can expect to measure is about 15 centipoise, and you could go up to 1.25 million centipoise if you were using the RV7. But of course, you're only ever going to use one spindle at a time. And if you look at one comparison of one to the other, it's really just about 2 orders of magnitude difference that you have to play with. So that's your viscosity range. Now, if we carry on about that and think about all the other materials you can deal with, you've also got the RVT, the HA, and the HB, etc. And what you're seeing is, of course, we're getting some subtle differences in the speed limits of the materials the instruments can be used, but we're measuring larger viscosity ranges. So what the hell does this really mean? Well, the best way I could think of comparing it was to show you these 3 samples. These samples are actually measured on a discovery called Rheometer. We'll come back to that later. They are the black line at the bottom, the lowest viscosity, has a viscosity higher than water, but it is a very low viscosity Newtonian oil. The blue one represents golden syrup, something you're familiar with from the kitchen, and again, it's a Newtonian material. And the top one, the red one, is actually a room temperature polymer melt. It's a low molecular weight, so it is a liquid. It's still pourable. However, we're not going to get too involved in polymer melts in this example. But what's interesting is if I consider the actual physical torque ranges of the instruments, and they're put there in the bottom right-hand corner, and put those on the graph, what I see is clearly that the LV can't actually measure the low viscosity materials. It doesn't matter what spindle. Remember, the top and the bottom ranges are based on the spindles used. So it doesn't matter what I do, I can't measure a low viscosity fluid. If I take the RV system, then I've got even less chance. But what I can see is that I'm maps in close to the middle or to the low end of the range for measuring golden syrup. So I might be using a mid-range spindle. If I choose the HA or the HB systems, again with their torque ranges, I can measure the golden syrup, and only with the HB could I have potentially the chance to measure this very thick gloopy material, which might have similar consistency to, say, maybe caramel or something like that. However, we don't just talk about torque ranges. We talk about being able to change the spindles, but more importantly, the speeds. So I'm actually considering the speeds of these RV spindles on these things. And on the bottom now, we've got RPMs, which is the typical speed setting for a Brookfield. And what I put on here is if we look at the values, these are the ranges we expect to be able to measure between the viscosities, again, reminder. But the speed range for an LV is there. And again, clearly shows that we can measure the golden syrup, now in purple. So could the RV. And in fact, when we come to look at the HA and HB, we can see that, yes, we might just be able to measure the golden syrup, but we can't actually reach high enough to measure the PDMS, the polymer melt, purely because that sample misbehaves. It starts to really not represent a sensible sample by any change. It will basically create a hole and cavity. So what we've got is that actually, if we consider speed or consider the torque ranges, we have a little complicated story to make sure we hit the right region to be able to get a decent measurement. Now, take this a little bit further. If we take an example of 2 materials, one known to be good and one known to be bad, the good one is blue, pinky one is bad. What we see is if you do a measurement, a pragmatic approach at one speed, you basically get very similar answers. You can't really see a great reproducibility because the numbers are all over the place. And then basically, because you can't define shear rate, you can't really represent it to a real world thing. So what we've got is a comparison which is sort of more or less a random number generator. That means if you're in R&D, you can't really measure any random behaviour needed to optimize your new formulation. You certainly can't troubleshoot any problems. If you're in a QC lab, I challenge you to be able to differentiate between a good and a bad batch. So as a result, you'll end up sending samples through that pass your QC spec, but actually get returned because there's a problem further down the line. So the next logical step is to actually deal with a theoretical school. Now, Brookfield claim the theoretical school is where they appreciate that there is actually shear thinning behaviour, non-Newtonian fluids. However, they also do not define the shear rates. They basically say that any user will probably say, I know the data isn't academically defined, but I keep that in mind and treat a multi-point rheology information as it were. So what we do is they've expanded the portfolio to do different things, multiple speeds, but realistically, they're just measuring multi-point viscosity, again, the same way as they've done a comparative thing. With no shear rates defined, you can't really apply Newton's law of viscosity accurately, so you can't really link it to anything that's other than pragmatic. But you could start to see trends in whether the sample is actually shear thinning behaviour. Still got to be cautious now about the required base unit, the spindles and applied speeds. And of course, now you should really be starting to think about temperature control more than just measuring the temperature. Now, I haven't got an example on that one, you'll be pleased to see, because I want to step straight onto the academic score. And that is where you actually use defined geometries, like the Brookfield-Wells Brookfield cone and plate, or the CAT 2000 viscometer, or the RSX or RSOs. These are systems that use cone and plates or coaxial concentric cylinder systems. And the reason they use these is that they now have a defined gap. That gap would have been something very similar to that white band you saw in my video with Willenden or food dye. It has to be smaller than that, so you really do know how much sample is being sheared. And that gives us the ability to define the shear rates and so apply Newton's law and actually get a real viscosity value. Again, still got to consider the base units and the geometries, but now it will be a case of maybe using a cone for higher viscosity materials and concentric cylinders for low viscosities. And of course, what we're now doing is we started to move up in price as well as performance on the Brookfield scale. So remind you again that if you take a sample like a standard viscometer and you do a rotation on it, there's a band there that we see we deform, we measure the viscous drag from, but as I showed in my little video, there's a white band measurement. Other than that, the rest isn't deformed, so we really can't define the shear rates. So as a result, we've got no analytical treatment for complex fluids because there's a complex flow pattern there. We've got relative values only. There's no real meaning to that, it's just comparison. And we have poor reproducibility. But if we have defined geometries like cones, parallel plates, or concentric cylinders, we can be very quantitative. We can have a physical meaning, so we can define the shear rates at different shear conditions. And we tend to find that we get great reproducibility. So let's take that third school onto the example of the good and bad sample here. And what we see is the viscometer range does show a trend of the samples showing shear thinning. The viscosity is dropping as you're increasing shear rates. However, you can't really get a very wide shear rate range. So we still can't predict what the sample might be doing at spreading or dripping. All we're doing is maybe extrapolating, assuming it's like a straight response. So we still can't really measure the relevant behavior needed to optimize our new formulation for storage or for applying. We can't troubleshoot some of the problems as a result. And we can still really barely detect differences between our good and bad batches. So I would like to introduce you a fourth school. I would like to suggest the fourth school is actually the best. Have a term you like, but the best approach to understand everything you need to know about your sample for all occasions and applications. What do I mean by that? Well, I'd like people to want to adopt the fourth school as people who want to measure and differentiate between their samples, to consider a wide range of processes and applications, therefore shear rates, etc., whilst finding it easy to do with great accuracy and reproducibility. And with these defined shears and conditions, they can predict samples' material properties at things like on storage and dispensing, mixing and pumping, and finally, the application conditions. And if you can do all that all on one instrument, and maybe even with one geometry, so you can reduce any potential human errors where, there could be that you mixed up the geometries or anything else like that, or haven't quoted which viscometer model you're using, we can basically ensure that whether you're in one lab or sites around the world, you'll all get talking the same talk. You're giving the same information. So I've mentioned the word, or suggesting now that we're really bridging the gap between a viscometer to a rheometer. Now, ChatGPT will describe a viscometer measuring a single viscosity value at one condition, whereas a rheometer can measure viscosities over varying conditions and more behaviours like elasticity, yield stress, thixotropy, things I've already perhaps mentioned in the past. The viscometers can measure more over wider real-life conditions. It can look at critical performance behaviours like dispensing or surfboard levelling, storage or whatever. It can define these things called viscoelastic properties to actually reflect the microstructure and impact things like sensory perception or storage performance. And it can look at just not only liquids but semi-solids and even follow gels. So let me introduce the Discovery Core Rheometer. That's what it looks like. And I'm sure you'll, hopefully you'll find enough interest to follow up on this. But realistically, the idea is it's a superior, easy to use for all different operators. The reason it's so simple is it has a touchscreen with prompts and user interface on it. So the user is actually highlighted a screen that shows them something to do. Once they've done it, they go on to the next step. Because it's so easy to use, you'll find that there's less training time required. So anybody can start running tests from day one. A short overview, maybe a dummy run, and then off and running. And the key point is that if you already have rheology in your business, you can directly transfer methods down from R&D to QA and QC. Because the instrument is a much more powerful device, you can start to do more complex testing as well, and still keep it simple for the operator. At the other side of it, it's designed to be high performance and throughput. It will give you a better measurement than any viscometer over a wider range of conditions, etc. It has built-in rapid, precise temperature control, and the geometries are auto-recognizing. So when you put a geometry on, it recognizes it, and it will actually tell you if you've got the right or wrong geometry for the test you want to run. Now, I mentioned temperature control there, and what I want to highlight is some examples we found from just having conversations with people when we were developing the DCR. Some of the people mentioned that they were not really thinking about temperature. We asked them the question, is the sample temperature same as the room temperature? Well, yeah, it's temperature at ambient. But does the room temperature change? Well, yeah, between the years and seasons, so viscosity values will change. Oh, never thought of that. And basically, is the product used at anything other than room temperature or different room temperatures because it's used in different countries in the world? An example for R&D was a company that was using lubricants where basically they wanted to study the flowability at ranges of temperatures. What they noticed was even with the temperature control on the viscometer, it took about an hour to get the stable temperature of the system. So if they then wanted to do multiple points for a flow curve over a range of different temperatures, the testing could take days. In a QC lab, they bring samples straight from the mixer. They've just made it, so it's still slightly warm. What they find is that they want to bring the consistency, they want to bring it down to 25 degrees, the chosen room temperature. Of course, this takes time and slows down throughput. In the meantime, they can't actually ship the product that's on the processing plant until they've given them the thumbs up. It's passed the testing. So as I say, the core Rheometer actually has built-in temperature control. That means your QA lab won't have to be waiting for samples to cool or heat up, etc. What they've got to deal with is if they're going to cool it down, they can cool it down by the Rheometer itself, and that can reduce the testing time by about 70%. That means your plant isn't waiting for things to be tested. They're being tested, hopefully passed, and then you're shipping the things out the door. If you're in R&D, then of course, if an example with the lubricants, if it takes hours to equilibrate, it's slowing the development process down. But with the Rheometer being built in Peltiers, you can get the temperature control very accurately, and you can do a whole range of testings within about 1 hour, rather than maybe 2 to 3 days. I also mentioned that we can measure over a wider range. Well, here we go back to our examples of the pink and good and bad samples. And what we can understand is the torque sensitivity is much greater on a Rheometer than it is on a viscometer. It's about 1,000 times more sensitive. That's because we're using air bearing technology rather than ball bearing. We're actually using a drag cut motor rather than a torque spring, both being calibrated, of course. So the DCR torque range in dynes per centimetre to relate to the viscometers is 6 decades of range, whereas most viscometers struggle to have 2. We have accuracy of viscosity values and precision to detect the differences because we get confidence about reproducibility. We can apply a whole range of shear rates from low to high. So we can now simulate dripping, we can simulate spreading, and we can actually now see one complete flow curve and see the sample shear thinning. We can start to see the hints of the first new zero shear plateau and the high shear plateaus. So we know that the system is not going to change much more than that. And we can actually do other testing. We can do yield stresses or time dependency like thixotropy, or look at viscoelasticity. And the insert there actually represents frequency data from materials to show how the sample changes on timescale. I won't go into that in great detail yet, but realistically what we're looking at is trying to understand the structure of materials, and hopefully that's enough to give you a taster for why you would want to use a rheometer. So let's go back to measuring those samples we had before, the PDMS, the golden syrup, and the S6 oil, but I've now added 3 other samples. The blue one represents the concentrated fabric conditioner that I used in the example of the video. The black one is a ketchup, and the the green one is a representation of a tube of gel that you might get for injury sprains or anything else, an isoproofing gel. Now, all of those come out of tubes and have shear thinning properties. And again, I'm going to do the same scenarios. All of these were measured with one instrument, the DCR, with one geometry, a 40mm 2-degree cone. No faffing about, just that configuration. Now, if I start to look at the LV, again, what I've confirmed is I can't measure the low viscosity, and I can just start to see perhaps the low shear end of the concentrated fabric conditioner. Maybe I get 2 points to hint that it's shear thinning, but I don't get anywhere near the ketchup or the gel. If I go to the RV, then maybe I'm moving more towards the end of actually starting to see the structure of the viscosity in the bottle for the ketchup and the gel, but I can't measure it much more of the shear thinning. So I don't get any ideas of whether it changes much. And in fact, I might have even come to the conclusion it was Newtonian, because I don't get much of that hint of that drop in viscosity. If I look at the HA and the HBs, then again, I'm getting different segments of the ketchup and the gel measurements. I'm not being able to measure things like the fabric conditioner or the low viscosity materials. So I'm a bit limited in what I can measure. Again, I have to choose the right viscometer model, whereas with the DCR, I just chose the DCR and it does everything for me, from low viscosity to high viscosity. If I consider the same way about the speeds, then the speed range is 12 decades for the DCR. It can do incredibly low speeds and very high speeds. So we've got, again, the LV will sit in the middle at the high end here. And again, we can start to see something of the shear thinning behavior of the ketchups, etc. We can see more with the RVs, the HAs, and the HPs. But again, we see the fact we're actually struggling to cover a whole range of one sample. So I'm not getting all the information for the ketchup, the gel, or the fabric conditioners. Now, we better talk about the DCR in a bit more detail. So here we go. The key point about making it easy and friendly is we use this thing called Rheoguide. It's basically an interaction where it ensures that people can walk up to use it. No real training necessary, just maybe a dummy video to watch or whatever. They can have guided operation, taking them through step by step what they have to do. There's a validation throughout, because you can run scripts to actually, methods to actually confirm the instrument is in spec before you do any testing. You get rapid results and you synchronize the testing. Now, if you want to know more, you can go to our website and actually sign up for a demo if you want to, and that will give you more details. But I'm going to give you some examples now. So what is Rheoguide? Well, it's a walkthrough the process of like an SOP that you might experience. You don't have to make any decisions. You just literally follow a set method. You can't skip. You can't jump through the procedure. You just follow each step, step by step, filling in examples, the instrument, the sample details, loading the sample, trimming the sample, because we do want to make sure you get decent measurements, starting the test, then viewing any results that you're interested in, and then just simply cleaning up. Now, what we've got down the bottom here is what is called a Rheoguide simulator. Again, something we can make available to you, but to give you an idea of what's actually happened with that system, it's a dummy run I'm going to just show you here. This is a Rheoguide video. So let me just start, hopefully this starts. Oops, sorry, I've just skipped it. Let's go back one. Start it again. Please start. Nope, it's not going to start. Come on, you do want to start. Technology is a wonderful thing. Let me go back one stage. Go forward. There we go. We've got it back in. So we're using a method of viscosity at 10 reciprocal seconds. You can simply see that you're typing in the details of the material, and then you can just say, okay, select projects, etc. Prompted to load a sample, either with a pipette or a syringe. At this point, the sample head will come down and squeeze your sample, and then it's ready for trimming. Once you've trimmed it, you'll verify, you'll say, yes, I'm happy with it, press go, and it will do the testing. At the end of the test, you might get some information and following analysis. So here's an example which tells you the viscosity at 10 reciprocal seconds was 321, and then you'll get a prompt to say, basically, we're going to raise the head, The head will then raise to give you an ability to clean the sample. It prompts to remind you how to clean the sample, and literally, as you see, you just wipe things clean. And you can go either back to the next test, or you can go back to the main panel and choose another set of tests to do a different type of method. So what I want to do is give you an example of a flow test. I've put down the screenshots from that simulator down the left-hand side because you won't be able to see the touch screen accurately. And let's see how it works.
So let's see the DCR in action. The DCR unit here is sitting here on its own, ready to measure this jar of mayonnaise, which we know is a shear thinning material. The chosen geometry is already attached, though it will check to see that you have got the right geometry on. You'll see that perhaps later. And I've left the computer screen in show because we are running Trios software in the background to collect our data to do the analysis or anything else, just like Brookfield would run their 360 software. So what we're going to do is we've got a choice of screen to choose various test methods, and I'm going to choose to use viscosity multiple points. I'm going to run a number of shear conditions and see what the viscosity is of those conditions. And what I got a choice here is sample details, project and operator. And just to give you an example, if I choose the operator, I could assign new labs, departments or whatever using the instruments in advance or now. Could have a QA lab, could have development or anything else like that, but I'm just going to stick with QC lab. And what I'm going to do is in the sample details of the touchscreen, just literally type in the word mayo, go OK, and then when I'm happy, I go on to the next step, and it will prompt me to load a sample. So I'm going to take a sample of mayonnaise from the jar, put it on the lower plate, simple as that. We don't need too much, but it's very difficult to load a sample with a spoon quite accurately, so we'll go with that. Now you'll see that as I've pressed the go button, the sample will now be squeezed between the geometries, and we'll be looking at giving the correct fill for that geometry. Remember, this geometry is a well-defined geometry, so it's accurately going to measure the viscosity at a known shear rates, and so we get a prompt on the screen to do a trimming. So now what I do is go round, removing the excess sample. Just a simple case of guiding the trimming tool. Could be an end of a spatula, an old business card or anything else like that, but just literally a straight edge that can go round, and you use to rub it against the geometry and the lower plate to give you a reference to it. And when you're happy, go next, and you'll get a prompt to verify that you're happy with the load. And when you are, you simply go yes, and then the test will start. So the instrument is off doing its testing, and as I said, what it's going to do is it's going to do a series of different shears and measure the viscosity each one. It's actually going to do a 15-second test at each individual shear, a bit like the Brookfield single steps or multi-step testing as well, just a simulation of that. So what we're going to get is it's going to apply a shear for a length of time that's 15 seconds, and it's going to average 10 seconds worth of data to quote me the viscosity. Now, because it doesn't look that exciting in the video, what I'm going to do now is I'm going to turn on the computer screen so you can actually see what's going on in the background to understand that what we're actually dealing with is that we are measuring the viscosity of the material. And you might just see now a blue line representing the viscosity dropping over time. Now I can choose to plot these. These are currently being plotted in centipoise. I would normally plot them in Pascal seconds because I use SI units, but because Brookfield and most viscometers tend to focus on centipoise, I've left it at that. So it's very clear that this sample is a shear thinning material. The viscosity is dropping as we go from higher shears. We've got 1 or 2 points left to go. We've got a status bar to tell us how many points we've got. As I said, it's not essential that you have the computer screen on. It's just for the sake of this video, it gives us something to talk about while the test is running, because otherwise you really wouldn't have a clue what's going on. So 2 more points to go. Final point, and then our focus will switch back to the touch screen of the DCR, where it will fit the analysis and give us the results on whether it's in spec or not. So what we've got here is it says, congratulations, the experiment is successful. It's given us a prompt to say that at 50 reciprocal seconds, we're within range. We're towards the high end of the range at 5 reciprocal seconds, but we're still in spec. Obviously, you define the spec ranges based on your own information. QC specs. If I go to next, it will then suggest that I'm going to raise the head, so I literally will raise the head. And then we're in a position ready to be prompted to clean the instrument. Now, because we're only using a very small amount of material, it's so easy to clean. So once this is fully raised, you'll get a prompt to clean it. And all we need is a tissue. And so we just wipe the lower surface clean, and run it around the edges and just tidy up. That's that clean. Fresh tissue, take the top. Doesn't matter, you can touch this. It's built to be robust, so any operator can handle it. Just literally wipe it clean. And you're then ready to say, good, I'm happy.
So as mentioned there, keep an eye on the time. You can have this touchscreen giving an example to say you've been successful, but you can take down the numbers. And in fact, Trios will allow you to export values if you wanted it to some sort of LIM system or JSON export. But let's not get too involved. Or you could unfortunately get a result where you get a fail, a big warning to tell you about the spec. In fact, that sample of Mayo 3 actually was catch up just to make sure it failed. I also mentioned that the DCR has the self-recognition geometries, and if you try to use the wrong geometry, unlike with a viscometer when you can put a different spindle on and get it confused, this system will actually recognize that the wrong geometry is attached and prompt you to put the right one on. So it's idiot-proof. So what I want to do now is just remind you that the Rheometer is on the higher end of the productivity performance-wise scale, and that's because it can do oscillation testing. That means we can look at things at a sample and elastic. So when we do an oscillation, we actually operate the geometry backwards and forwards. We wobble it. And we can see that if it's purely elastic, the sample follows the geometry. If it's purely liquid, it lags behind and have a thing called a phase angle between 0 to 90. What does that really mean? Well, I'm not going to give you a masterclass in rheology. What I'm just going to say is we're going to look at parameters like G prime and say that's how solid-like the material is. G double prime is how liquid-like the material is. And I've given you examples there of a bouncy ball and a tennis ball, where the tennis ball doesn't bounce as much because it has a much higher viscous component. So it acts like a little bit of a liquid. Now, if you've got materials that are G double prime dominant, they will appear like a liquid. If they're about 50-50, then they act like a soft, solid gel. And if you've got G prime becoming dominant, then the sample will behave like a solid and stay put. If it gets too dominant, it could actually become brittle. So again, the DCR itself can be used to do similar testing, but in this case, as the video shows.
So let's look at the DCR doing other types of tests that a viscometer can't do. We're now going to ask it to look at the structure of the mayonnaise. We're going to see and explain why the sample that we've just seen shear thinning, when it's on a spoon, wobbles. There's a structure here. We know that if we shear it between surfaces, it will break down and shear thin, but it acts like a wobbly gel. So what I'm going to do is a yield stress technique, and we're going to follow the same sort of prompts that we've been getting in before. So I'm now going to call this.
So in the interest of saving
now
some
the
time,
test is finished. What we can see is on the touch screen we get values for the crossover point. We've got it in SI units and CGS units, your choice. And if I put the screen on, you'll be able to see the results. And the graphic shows, hopefully once that monitor label goes, that what we've seen here is that the red line represents how solid-like the material is. The blue line, how liquid-like the material is. So this case, this sample is very elastic dominant, hence why it's wobbling on the spoon. The phase angle, the ratio between the two, is down here at around 8 to 10. And then as we see that the sample breaks down, as we yield, then we see the rapid increase in the phase angle. And when the phase angle goes through 45, G prime and G double prime cross over. So the sample becomes, instead of solid dominant, liquid dominant. So it's physically changed its state of nature. And as a result, you can imagine that the sample will behave now more like a liquid than it would as a solid.
So with dynamic testing possible on the DCR, not possible on any viscometers, you can apply and control a sinusoidal deformation that can be at a different amplitude, frequency, or temperature, or you can just watch time go by. That means with an amplitude sweep, you could define things like how robust the material structure is, just like I've shown you in that video. And actually that can be used to look at the quality of dispersion. And here's an example you'll see, just showing that you keep taking samples at periodic mixing points. You can actually see that the value of this plateau, that red line, starts to go up and it starts to plateau off a constant value. You've made a final dispersion. We take frequency, then we can see a sample fingerprint, but we can also predict extreme timescale performances like low, long timescale creeps or stuff like that. So like a pressure sensitive adhesive on a post-it note, how long will it stay up? Or stability, or a simulation of maybe a car wheel going over something. We can look at transitions. We can look at defining the glass or the melt temperatures, and we can also look at how the temperature changes in the transition region and the rubbery region, so the balance between G prime and G double prime, to make it understand that something could be easily deformed, turned into a certain shape, and it will maintain that shape. And finally, we can just follow things like cures, gelations, or drying processes. And we can see in this example a full cure of a material like a 2-pack epoxy glue or super glue. And for those who are in the coating industry, whether it's topicals, creams and lotions, or paints, inks, or anything else like that, then you should be interested in being able to probe the structure of a sample at rest. So see how structured it is. G prime is red, so that's solid dominant because it's greater than the blue line here. So if we look at the material, the red is greater than that, and the viscosity is here. And if we go into the next step and show what's the next stage is, we then have an application where the sample becomes very liquid dominant because it's got to be easy to apply and the viscosity is dropped. And then finally, after we've stopped applying it, we need it to go back to recover its structure so it stays put. Recovers too quickly, you could have brush marks or orange peel or anything else. If it covers too slowly, you've got a lovely finish and leveling, but the panel is actually the stuff stripping off the edge of the panels. So realistically, what I want to point out there is that's something you can do on a DCR that you can't do on anything else other than other standard Rheometer. So if you're into paints, inks and coatings, just a summary, I'll remind you that you could use the Discovery Core Rheometer to look at the flow properties at different shear conditions to understand processing behavior and application simulations. You can use oscillation on the far right hand side to look at quality dispersions, structure rebuild, post-application and fingerprint it. And in between, you've got a technique called creep, which I haven't discussed, but that's where you can simulate low gravity driven processes. So you can predict shelf life and post-applications behavior. And the same could be said, exactly the same for personal care with soaps, lotions and cosmetics. The same for pharma, topical and oral and injectable systems, and foods like sauces, yogurts, spreads and pastes. And even if you're into batteries, you can do about your slurries, your anode and cathode. So thank you for your time at this point, and I'd just like to remind you the reason that you would want to go from a viscometer to a Rheometer is because of the sensitivity. You've got a greater range of torques available, so you can really start to differentiate between formulation changes for R&D and screen more successfully batch-to-batch variations in QC. You have a very large shear rate range, 12 decades of speed, so you can really optimize and control product performances and understand how it's going to work in real life. And if you're going to look at the QC environment, you can understand it's QC for application, for storage, or whatever. And with built-in temperature control, then you can modify and control and investigate your materials behavior in varying environments and make sure you've got consistency results throughout with a faster throughput, as well as having more insights into product performance, viscoelastic structures, and things like storage. All in all, the system is easy to use and has great performance. Finally, there's some additional YouTube video links that I found, the Brookfield ones I mentioned earlier. I actually found the Institute of Personal Care in Australia gave a nice example of the pitfalls of using a viscometer. And I'd recommend perhaps talking to people like the Centre of Industrial Rheology, where there's some friendly YouTube videos to try and introduce this concept that's confusing most people of rheology. And of course, our own videos on our own website. So for them, I say thank you very much. And I'll now wait for somebody to tell me if we've got any questions, or I'll view the chat myself.
Thanks, Peter. I really appreciate that. Have we got any questions from the audience? There's none in the chat so far.
And just come on with, if samples settle to the bottom over time, what test should I do on a rheometer to find out if the suspension concentration formulation redisperses after storage? Wow, that's a mouthful. Okay, so just to finish off, sorry, Don, I'll see you came on camera. I'll just wait for you a sec. Realistically, what you're going to look at is that you could talk about the amplitude sweeps, giving you an idea of this quality of dispersion, because if you've redispersed everything the way you should have done, it won't get any better no matter how much more you stir it. And then once you've done that, then I'd suggest you do creep testing to understand the stability and predict how long you've got before the sample starts to have a problem. Okay. And obviously talk to me offline, send me an email if you need to. Donna.
Forgive me if I missed this at the start, because I missed the initial start of the presentation, unfortunately. But in terms of this instrumentation, do you have any reference customers that are using it? In particular for me, for my remit, is food, beverage and environment. So I was kind of interested in where you might have positioned this in terms of that market. I could imagine maybe PepsiCo R&D would be interested, or, you know, that kind of level. But I just, wondered if you had any examples you could share.
It's an interesting question purely because people like PepsiCo and many other food industries already have our rheometers in their development and R&D labs. And obviously, we're very keen for them to consider having a cheaper instrument like the DCR in their product plants or anything else. So many of the cases that I've seen people have, there's some well-known confectionery company in the Slough region that tends to use rheometers in both R&D, but also in QC, and have done for decades. But the key point is the DCR was launched tail end of last year. Sort of realistically, it's only just starting to hit the shelves and get people really interested in. So I would love to say, oh, we've got a lot of references, but what we're finding is that we do our first port of call is to probably make awareness to people that there is something new out there that's a little bit friendlier on the pocket, because most people obviously think viscometers are nice and cheap and cheerful, but really it's got to remind themselves that it perhaps doesn't do a job that they want it to do. And a rheometer like the Discovery Core rheometer is more than capable of doing all the simple testing and the more complex stuff without making it difficult for the user. But realistically, there's two approaches. It's getting people who are already familiar with rheology and appreciate the benefits, and having to transfer that technology down to their production floor so it's easier for them to ensure that they've got uniform things and testing around the world. And the other side of it is to make people that are a little bit scared of rheology take that next step upwards to realize that they can actually be sitting there going, you know what, it takes me far too long to do this test, or this doesn't really work as well as I would like it to. Perhaps I should try something. And this is the taster for them, the next logical step for them, because what we've tried to do is introduce something that's, it's very powerful, but also at a price that suits most people, we hope.
Great, thank you.
You're welcome.
Thanks, Peter. We've just got another question as well around the typical timing for a test in QC. How long does it take to run a test if you have a method developed? I know it will vary depending on product form.
It really would. I mean, the reason I tried to run the videos, and I'm sorry I went on over a little bit, was I wanted to try and give you an example of a video, a test running. I ran it for its full course just to show you that measurement. But of course, the length of the test can vary depending on how many data points you want. So again, it's a little bit sort of how long's a piece of string question. But realistically, if I want to get the flow curves I showed where I saw the low to high shear, etc., the full flow profile, you're talking about a test method that might take maybe 10 minutes. The rest of it is the typing in and the trimming and whatever, which probably adds another 5 minutes to it. The luxury is temperature is very rapid. Control cleaning is a lot easier. And all I can point out is that whenever I watch any videos for people using viscometers, they usually have to put something in a beaker, in a jar or in a water bath to stabilize it at temperature. Then they take it out, then they have to put a guard in, and then they have to put the geometry, and then they attach it, then they do a measurement and find out they got the wrong spindle or the wrong one, and then have to start all over again. So what we're trying to do is make it fit for all purposes to cover a whole range. So I would say most QC testing, the concept I've always been aware of because I've worked in the industry for so long, is QC wants a test that's done in 2 minutes. Let's be honest, they want the answer straight away. And to do that, then you have to take a compromise in terms of the amount of information you're going to get. But maybe 2 to 10 minutes is a fairly typical time.
Thank you, Peter.
You're welcome.
Thanks, Peter. Just last question from me. Just thinking of our SLS customers, a lot would have Brookfield viscometers. Is there a way to integrate the Brookfield data into the DCR?
It's a nice, yeah, that's fine. The interesting thing is, as we said, it depends what type of Brookfield you're using. Because if you're using the RSX or the oscillation-based system, you've got a fighting chance because you're using defined geometries. If you're more using the pragmatic approach, then to be honest, you've just one up from stirring it with a spoon. So the value is very, very dependent on the conditions you've used. However, it's been interesting because of conversations we've had with a few people. We've actually tried, and as you see, I can actually put a Brookfield configuration on a Rheometer and start to actually correlate it to get some bridge between that gap. Because yes, Brookfield effectively has its own number. It's a random number based on what it measured at that time, that day, etc. Not belittling it, but it is a comparative test. So the only way we're going to bridge people's confidence is to get that comparative test working and then actually start to tune it down to optimize the measurement so that it really is giving something meaningful for all occasions. So that's what we're looking at, and that's what I've been trying to do in the meantime. And hence why I showed you some of those slides to try and give you an idea where we are on the Brookfield scale and why you don't have to worry about being on a Brookfield scale, because you can measure absolutely everything in one go with one instrument, with one geometry. Make life simple.
I like that. Thank you.
Gemma, you put your hand up, I believe.
Hi, yes, thanks, Peter, for that. It was really, really useful hour. Thank you. More of a practical question from me. You showed that you can measure the really low viscosity liquids on this instrument as well. How would you practically load that onto the sample? You know, the mayonnaise looked nice and straightforward, but how would you then be trying to load a really low viscosity sample?
Sorry.
No, you carry on, please.
With the things, samples like water, milk, the S6 that I showed you, the natural tendency is to use a pipette, a disposable pipette or something. It's not ideal because you're going to, if there is any structure, you could be damaging it. But in that case, with the oil or milk or anything else like that, there's such a low degree of structure that it's easy enough to use a pipette and you just then get the right volume. You don't even have to worry about trimming. So it's a lot easier to work with samples that are very, very mobile. It's when they, like the fabric conditioner, actually is laced with micelles because of the surfactants in it. And that has a lot of structure that most people would miss because they've damaged it while loading it. So the key point there is just to have be gentle or give it a couple of minutes before you press go to give the sample a chance to recover its structure.
Yeah, okay. And is that kind of an analogous geometry to a parallel plate on a Rheometer? Are they very similar?
Yeah, no, I mean, basically you can imagine that with the cone or the parallel plates, there's different configurations for the Rheometer to fit. Obviously, most people would probably prefer, if something's pipettable, to put it in a cup because then it seems to be contained. And as a result, then it's just a case of just filling a cup. That's even easier. And so again, there's different configurations. The DCR does have concentric cylinders as well, but I just try to keep it simple by using one geometry to cover a vast range, as you can see. So something very mobile and pipettable to something that basically you can mold with your hands like plasticine.
Yeah, okay, great, thank you.
Thanks. You're welcome.
Well, I'm just conscious of the time. So what we'll do is we'll follow up with a recording of this session and include Peter's details as well. So if there are any more questions, we can take those offline and get those answered for you. But thanks again, Peter, for that presentation.
Thank you, everybody. Thank you for your time and attention. And I hope we've found something useful for you, or at least sparked a conversation with your colleagues. And as Katie said, feel free to come back to us or we'll look at the websites or etc. to find out more. Okay,
perfect.
Thank you, everybody.
Thanks, everyone.
Take care.
Thank you so much for attending, as well as for organizing a Peter great presentation. Bye.
Bye, everybody. Take care. Thanks, Katie. I appreciate your effort and staying online. I'll see you now.